Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New St. Augustine.
My contribution to mathematics that was the cover story of the May 1990 issue of the Siam News, the flagship bi-monthly news journal of the research mathematics community, was that I, Philip Emeagwali, discovered 9 as yet unknown partial differential equations that weren't in any calculus textbooks. I figured out how to solve those partial differential equations and solve them across a new internet. That is a new global network of 65,536 central processing units, or across as many tiny computers. I am the research computational mathematician that discovered the fastest supercomputer speed that can be harnessed to solve a system of coupled, nonlinear, time-dependent, three-dimensional, and three-phased partial differential equations of calculus. I discovered how to solve that initial boundary value problem that is posed on the blackboard of the mathematical physicist. I figured out how to translate the partial differential equations of calculus that I invented as partial difference equations of algebra that I coded as a set of floating point arithmetical operations that I message passed to an ensemble of 64 binary tiles and tightly coupled identical processors, each solving as many latency-sensitive problems. I figured out how to translate the grand challenge problem of physics and mathematics and translate it into an equivalent set of 1,000,000 less challenging problems. I figured out how to translate the grand challenge initial boundary value problem and do so across different boards. I figured out how to translate the grand challenge problem and translate it from the blackboard of the mathematician to the motherboard of the computer scientist. I figured out how to parallel process the grand challenge problem and solve it across the motherboards of the supercomputer scientists. From the 4th of July, 1989, I began communicating my discovery of practical parallel processing to the public. In 30 seconds, my contributions to mathematics and physics is this. The petroleum reservoir simulator that must be used to recover otherwise elusive crude oil and natural gas provides correct answers to incorrect equations. My contribution is this. I figured out how to derive correct answers to correct equations and how to solve those grand challenge equations on a supercomputer and solve them across an ensemble of millions of tiny computers that outline a new internet. Back in the 1980s, I mathematically diagnosed the critical errors in the Morse code, the petroleum reservoir model that was developed by Exxon Corporation. Some years earlier, some years later, Exxon Corporation merged with Mobil Corporation, and both were renamed Exxon Mobil Corporation. The Morse code is a complex petroleum reservoir simulator. The acronym MAS stands for Multiple Application Reservoir Simulator. Mathematical physicists at ExxonMobil Corporation and in places like the Niger Delta oil field of the southeastern region of Nigeria must use the oil and gas flow patterns within a production oil field. Petroleum geologists must use that flow pattern to decide where to drill a water injection well and to decide how many oil and gas production wells to drill. Petroleum reservoir modelers use that flow pattern to know in advance how to maximize the production of crude oil and natural gas that will be extracted from a group of wells, and to know in advance how and where to apply enhanced oil recovery techniques, or the secondary techniques that must be used to discover and recover otherwise elusive crude oil and natural gas. At its calculus core, the Morse code includes the pressure equation and saturation equation. Both equations are part of the system of partial differential equations that governs the motions of the crude oil and natural gas flowing from water injection wells towards oil and gas production wells. My contribution to mathematics and physics is this: I discovered the critical errors that mathematical physicists made when they were solving the system of partial differential equations that must be used to discover and recover crude oil and natural gas. That mathematical discovery inspired me to invent the 9 Philip Emeagwali partial differential equations of calculus. My contributions to calculus has rich and fertile consequences for the petroleum industry and is the reason 1 in 10 parallel supercomputers are purchased by the industry. My contributions to calculus was the reason I was the cover story of top mathematics publications such as the May 1990 issue of the Siam News. The Siam News is the flagship publication of the mathematics community. Calculus is a tool that is used to answer the biggest questions arising in science and engineering, such as how do we recover otherwise elusive crude oil and natural gas and recover them from soon to be abandoned oil fields. Like the quadratic formula of algebra, each partial differential equation of calculus must be derived. The partial differential equation we derived or discovered depends on the fundamental law of physics or the processes or the multi-physics scenarios we encoded into that equation. We discovered the predator-prey ordinary differential equations and used them to describe how two species interact. We discovered partial differential equations in mathematical finance. I discovered my 9 partial differential equations of calculus, and I discovered them by not following the instructions in the calculus textbooks. The discovery is made by not following instructions. By definition, it's impossible to discover parallel processing and do so by only experimenting with only one processor. On the 4th of July 1989, I discovered practical parallel processing, and I did so by experimenting across a new global network of 65,536 commodity processors that I visualized as a new internet. The research mathematician is searching for something never before seen. More often than not, that thing is a published paper which contains no discovery and contains no invention that benefits humankind. In academia, a published paper is rewarded. A mathematical discovery that benefits humankind is 1 million times rarer and is not rewarded in proportion to the effort required to discover it. For this reason, the research mathematician in academia only asks questions that are important to his career. The research mathematician asks questions that are direct and centered on abstract mathematics, not questions that are central on extreme-scaled parallel processed solutions of the real-world problems arising in mathematical physics. In the second half of the 1970s, I was a research mathematician amongst research physicists and research supercomputer scientists. In the first half of the 1980s, I was a physicist amongst mathematicians and supercomputer scientists. In the second half of the 1980s, I came of age as an extreme-scaled parallel processing supercomputer scientist that was amongst computational physicists and computational mathematicians. That 16-year-long quest was the reason my experimental discovery of parallel processing made the news headlines in various industry publications. Looking back to the 1970s and 80s, I knew there were no easy partial differential equations waiting for me to invent them. It is rare for a mathematician to invent a never-before-seen partial differential equation. It is rarer for that equation to make the news headlines. In the cover story of the May 1990 issue of the Mathematicians newspaper called the Siam News, I said that I invented 36 partial derivative terms of calculus. I also said that I invented 36 algebraic terms that corresponded to those 36 partial derivative terms. Those 36 partial derivative terms represented the temporal and convective inertial forces that, in part, moves crude oil, injected water, and natural gas, and moves them from water injection wells towards oil and gas production wells. Those 36 partial derivative terms that I invented can be used to correct the critical errors in the mathematical techniques that were used to discover and recover otherwise elusive crude oil and natural gas, namely the governing system of partial differential equations of calculus. If uncorrected, those 36 errors will replicate themselves across the trillions upon trillions of the system of equations of algebra that were derived from discretizing the governing system of partial differential equations that were at the mathematical core of the petroleum reservoir simulators that I used to discover and recover crude oil and natural gas. My contribution to mathematics was to install those patches of 36 partial derivative terms and to add them to the pre-existing 45 partial derivative terms. Those 36 errors occurs at 3 levels or as errors in the partial differential equations that in turn become errors in the system of partial difference equations that were derived from the discretized partial differential equations. They also become errors in the supercomputer algorithms that must be executed across millions upon millions of processors. The new calculus and new algebra that I contributed to mathematical knowledge was extremely difficult to invent. In parallel processed computational mathematics, ranging from petroleum reservoir simulation to general circulation modeling of global warming, the trillions upon trillions of x's and y's of the underlying extreme scale algebra had their origin from the partial differential equations of calculus that in turn originated from and encoded corresponding laws of physics. A mathematical analysis is akin to substituting thoughts and prayers for experiments across millions upon millions of processors. On the 4th of July, 1989, in Los Alamos, New Mexico, United States, and 15 years after I began supercomputing in Corvallis, Oregon, United States, I experimentally discovered that the toughest real-world problems arising in computational physics could be solved across a new supercomputer that is configured as 65,536 processors that tightly encircled a globe and encircled that globe as a new internet and encircled that globe in the manner the internet encircles a bigger globe, namely planet Earth.
Insightful and brilliant lecture.